We have previously discussed the radial and transverse coordinate system, and we've talked about two different methods one can make use of to solve these kinds of problems. So let us look at the first example. We have here on the image, which is shown on the right, a rod OA, which rotates in a horizontal plane such that theta is equal to t cubed in radians. At the same time, the color B is sliding outwards along OA so that r is equal to 100 t squared in millimeters. We're asked to determine the velocity and acceleration of the collar when t is equal to 1 second. So since we have not solved a problem about that yet, I do not expect you to be able to solve this problem. Now I'll give you a small hint which would help you start off and give it a shot yourself. So this typical problem is related to the first method we've described in the lecture, in which we're given equations for r and theta as a function of time. We can easily then find the different components, velocity and acceleration, by simply taking the derivatives with respect to time. Now I'll give you a couple of minutes to give it a shot yourself, then you can continue the video to see the solution. The very first step is to write down what we know. We're definitely working in the transverse and radial framework. We are given theta is equal to theta t and r is equal to rt, so we know that we're dealing with case 1. So we need to take the derivatives and replace in the equations for Vr, V theta, Ar and A theta. We also know the equations of motion, or the kinematic equations, I would say, which gives us the values for Vr, V theta, Ar and A theta in terms of the different derivatives. So the next step is simply to take the derivatives. We have r is equal to 100t squared, so r dot is equal to 200t, and r double dot is equal to 200. Taking the derivative for theta, theta is equal to t cubed, theta dot is equal to 3t squared, and theta double dot is equal to 6t. Now that we have the different derivatives, we simply need to replace the value of t with the actual value, or the value we're looking for. So we're looking for the analysis of the system at t is equal to 1 second. So replacing t by 1, we have r is equal to 100, r dot is equal to 200, r double dot is equal to 200 as well, theta is equal to 1 radians, theta dot is equal to 3 radians per second, and theta double dot is equal to 6 radians per second squared. Now the next step is to replace these values in the expressions for Vr, V theta, Ar and A theta. And so we could get an expression for the velocity and the acceleration at t is equal to 1. So V in vector form is equal to Vr ur plus V theta u theta, where Vr is equal to r dot, which is simply equal to 200, and V theta is equal to r theta dot, which is equal to 300. Replacing that in expression, we get an expression for V in vector form in terms of ur and u theta. We can also find the magnitude of V by taking the square root of the two components. So square root of 200 squared plus 300 squared is equal to 361 millimeters per second. And to get the direction of that vector with respect to the r-axis, we can simply take the tan inverse of V theta over Vr. Remember, whenever you want to get the angle with respect to a specific axis, it's equal to the tan inverse of the second axis divided by the axis you're actually looking for. So it's V theta over Vr. And that's equal to tan inverse of 300 over 200, which is equal to 56.3 degrees. Similarly, to find A, we need to develop expressions for Ar and A theta. We know that Ar is equal to r double dot minus r theta dot squared, which is equal to minus 700, while A theta is equal to r double dot plus 2r dot times theta dot, and that's equal to 1800. Now that we have values for Ar and A theta, we can simply replace them in the expression of A. And so A in vector form is equal to minus 700 ur plus 1800 u theta. To get the magnitude of A, we can simply take the square root of the components squared. Square root of 700 to the power 2 plus 1800 to the power 2 gives us a value of A equals to 1930 millimeter per second squared. And to get the direction of A, again, with respect to the r-axis, we simply need to take tan inverse of A theta over AR. Again, notice we take A theta, which is the other axis as the numerator, and AR on the denominator. And so we get the value of phi is equal to 68.7 degrees. Now, if you want to draw A on the theta r graph, notice that A is directed towards the left since the AR component is negative. So it's facing the other side, the left side. The A theta component is positive, so it's upward. And so the A vector falls on the left-hand side.